Thank you very much for having me here today. And can you hear me? Yes. So we all been witnessing an increase in the use of application of machine learning in many different sectors. Almost a general belief that machine learning is the holy grail to true technological advancement. But is this really an inflated expectation? So if we look here at the curve, the hype curve, clearly machine learning and cognitive expert advisor are currently enjoying the high peak of this expectation. And in my view, this is to a great extent due to the tremendous advancement in the natural language and the speech recognition that is actually allowed to open up a new form of interactions between a human and a machine. But if we look actually, but there's much more to it when we talk about a rational machine. And if we look ahead to 2037, my vision is that an intelligent, rational machine should be a machine that is able to interact with humans in a human manner. For sure, the people will be able to talk to the machine using English, like we're starting to get used to it nowadays. But importantly, the machine will be able to understand the user feedback and use this information in order to perform lifelong learning. So that is my vision of what a rational machine is about. And in my talk today, I'm going to tell you how symbolic machine learning can actually help us to realize this vision. So how can we build a software that manifests intelligent behavior? Where are we today, and what is still missing in order to realize this vision? And this is actually the journey that I want to take today in my talk. So let's start from a very simple example to give you a little bit of an intuition what do I mean by human-like interaction between a machine and a human. So you might think, let's say that I'm going to try to buy a dress and I use a John doing a shopping online. So for sure, I will get overwhelmed with the many possible suggestions, okay? But what I really need are a few suggestions and the most suitable to me. Okay, so if you think about it, this is actually due because actually people think that giving many suggestions to humans is a good thing. But statistics have actually demonstrated that only 3% of the people that are exposed to a large quantity of selections end up actually buying something. And versus the 30% of people that are instead exposed to a much smaller selection will decide to buy something. So really, in order to have a human-like interaction between a human and a machine, what we actually need is a software that is able to learn my personal preferences, is able to learn models of personal preferences, use these models in order to perform personalized suggestion, explain and interact with people in natural language, and use feedback of people in order to improve over time the model, the knowledge that the machine has about humans. So the question is, if we try to open up now the problem much more broadly, and outside of the online shopping domain, if you like, we realize that the humans are actually facing decisions all the time. They face decisions in the personal environment, in the work environment, and in social environment. So the question is, how can we actually help provide a rational machine that can help people make the right decisions at the right time? So these decisions are actually made not in a controlled environment. They're actually made in a very chaotic environment. So the environments are complex. They have incomplete information. They are unpredictable. And the data from which the machine has to learn are actually full of noise. So the question is, if we had a rational machine that will be able to help people making the right decision at the right time, and will be able to select what is relevant for the people from the noise, this is clearly will be an opportunity to revolutionize the life of people, and for sure over time to also provide a massive impact to different industrial sectors in our life. So what we are talking here about are rational machines that can learn to provide the right answer to the right person at the right time. And really my vision ahead is that the rational behavior in a machine must be our ultimate goal. So, but of course, to achieve this great vision, there are still many obstacles that we need to overcome from a technological point of view. There are many technological challenges that we need to resolve in order to bridge the gap between the way machine learning is actually used today and this vision of a rational machine. So that there are many challenges, and what I would like actually to say here that in my view, the key important challenges that we need to address is how a machine should be able to extract semantics from the data. And how can it reason about the uncertainty and the noise in the data, and how can it, most importantly, learn and communicate, explain to the user what has been learned. And how can you use the user feedback then to support this idea of lifelong learning, so continual revision. So really what I'm advocating here are no machines that we can train a large quantity of data that aggregates information from the multitude of the population, and then once it's trained, is deployed. I'm looking at more rational machines that can be personalized and they can continue to learn and evolve the knowledge as the situation and circumstances change. Okay? So what is the technology that can actually help us achieve this kind of vision? So if we look at the area of machine learning, there are many solutions outside there, and academics are working very much, and company too, in doing that. So people talk about supervised and unsupervised. They talk about reinforcement learning, the very successful reinforcement learning. But what I would like to concentrate today is on two types of approaches of machine learning. One is called deep learning, and the other called symbolic machine learning. The former, we all know, has been very successful recently. Maybe it's one of the most popular machine learning technology nowadays. And symbolic machine learning is actually the area that I work in. Okay? So let's have a look, let's explore these two technologies and see where we are today and what is still needed in order to achieve and realize this dream of a rational machine. So if we look at deep learning is a data-driven machine learning algorithms. So it's an approach that is able to extract information from large quantity of data. It's based on the concept of neural network. Neural network are essentially a network that mimic the rational activity of the human brain. So these algorithms that can learn through activations of multiple layers of neurons. They've been extremely successful in various application domains. So we all know about speech recognition. So for instance, the example of the Amazon Echo. They've been successful in language translation. This is what is behind the Google Translator today. And they've been successful in image and pattern and facial expression recognition. But of course, deep learning is not new. So actually, neural network is not new. So the principle upon which deep learning are based on. They were actually proposed in the 50s, and already very successful algorithms were there in the 80s and the 90s. So really the question that we're asking ourselves, what has allowed the deep learning to make this big leap of success? And my answer here is big data and huge, vast computational power. So the type of computational task these algorithms are performing are highly demanding from a computational point of view. And the fact that we have now technology, computers able to do that, has actually allowed the neural network to make that leap. Okay? But, so the question is, can we actually rely just on deep learning to realize rational machines? Okay? And if you think about it, they are very good in extracting information for large quantity of data, no doubt about it. So they are very good at detecting, for instance, cats, the object of cat in a millions number of picture and video clips, right? But what I'm saying here, they're actually still far behind in learning the semantics that is behind the data. So they cannot really learn the general definition of what a cat is, and nor they can actually use this concept to learn even more complex semantic abstract concept. So the second drawback, in my view, about deep learning is the fact that they are black box. These are algorithms that are extremely effective, but they cannot explain what has been learned. They cannot reason about the mistake, they can, if you like, the errors in the learning and how they can revise and improve the knowledge they extract from the data. If we look now on the other end, at symbolic machine learning, this is at the far extreme of the spectrum of the machine learning. So they are not really data-driven learning algorithms, but they are knowledge-driven. So these are algorithms that are sitting at the intersection between machine learning and traditional AI, we can call it, right? The knowledge representation. So these are algorithms that can actually extract high-level abstract concept from data, but in particular from existing knowledge about the problem domain in which they operate. And because they're using this existing knowledge, they have the incredible advantage of being able to learn difficult concepts from a small number of examples, because they use the power of the existing knowledge on the problem they are trying to tackle. So as you can see in this graph, for example, we were able to learn models of personal preferences of people moving in a city, reaching 80% of accuracy with just 8 steps of interaction between the human and the machine. So we don't need many counterexamples here to reach a complex model, to learn a complex model. And the second really advantage of these algorithms is that the model they learn are actually rich symbolic representation of the knowledge, and therefore they are closer to natural language. So what is learned here can be expressed back in English to the humans. And they can actually use the human input in order to continue revising and improve the knowledge that they are learning. So they are not a black box like deep learning, but they're actually open box here. So, and really the question that you might ask now, oh, this sounds very great. So where is the catch, okay? And at the moment, symbolic machine learning are not very good, I would say, in scaling and learning this complex knowledge from large quantity of data, okay? So the question that we try to address is how can we resolve this problem? And we have been working in my lab in the area of symbolic machine learning, and I come from a city here in Italy, in southwest of Italy, and I came to Imperial, and my first postdoc in Imperial was in collaboration with the Verification and Validation Center of NASA in Pittsburgh, where we're actually working about developing a symbolic model representation of software of this International Space Station up there. So I came immediately to realize very quickly that these symbolic representations are extremely powerful in reasoning about a complex problem, but they are also very difficult to handcraft. So the type of challenge that I took in my research and in my lab has been how we can actually develop a new and advanced symbolic machine learning algorithm that are able to learn high-level abstract concepts from a few examples. And so I'm going to illustrate give you the insight of what really has been the breakthrough that we have made. And the kind of algorithm that we have developed have actually been very successful because we were able to combine reasoning mechanisms which are very typical in human beings. And these are called abductive reasoning and inductive reasoning. So abductive reasoning is the ability for an algorithm to understand the gap in the knowledge and make an hypothesis of what it is needed in order to explain the observation. Inductive reasoning is, on the other hand, the way of generalizing from examples and abstract away and get a general principle that can be used in other contexts. And in our algorithms, in our approach, in our breakthrough in research, we actually demonstrated that combining these two reasoning processes, we can be very powerful in the knowledge that we can extract from data. To give you an example of how, for instance, complex this knowledge can be, let's assume that we here have a set of labeled graph. And we give to the machine the label graph. We say to the machine, look, all of the machine knows are just the nodes in the graph and the edges in the graphs. So can you, for instance, guess what are the rules that the machine is going to learn here? There is very little information here. Okay? But from just 100 examples, we were able, for instance, to learn a very general concept, mathematical abstract concept of Hamiltonian cycles in graphs. These are cycles that start from any point in the graph, and they're able to reach any other vertices in the graph, visiting the graph at most once, exactly once. So a typical application of such a principle you might think about is if you have robots that needs to check the pay machines in the roads in a city. This can be a map. You want to make sure you visit every single node and not visit the most and really minimize the time in which you're doing that. So we are actually able to learn a sophisticated concept, and this concept is expressed back in English because of the symbolic representation of the knowledge that we can compute, exactly like it is written there on the slide. So, okay, so I've given now a little bit of brief overview that we have clearly lots of technology. Deep learning is very successful. Symbolic machine learning is also being very successful. And the question is, there is here a tension, clearly, between learning from large quantity of data, so scalability, how do we deal with it, and learning complex knowledge that can be used in human task activity decision making. So how do we are going to realize this vision of a rational machine? So what we really need is a way of combining together, developing new machine learning algorithms that combine together the advantages of deep learning and symbolic machine learning and overcoming their respective limitations. So the particular rational machine vision that I have is a complex, sophisticated, intelligent algorithm that really has to have three main features, characteristics, if you want. One is to be able to learn from large noisy data, but two is to be able to learn a complex concept. I'm not just happy with just identifying objects and pictures. And three, the concepts that I learned have to be expressed back in English so that the human can actually gain trust in what the machine is learning. And the machine can use the feedback of the human in order to improve what has been learned. So let's try to exemplify this vision. And let's try to push ourselves in 2037 and say, okay, if we are going to have such a rational machine, how can it help us? So let's consider, for instance, the life of Helen, and let's follow a Helen day from the beginning of the day to the end. So Helen wakes up in the morning, and then the first thing that happens is greeted by her true personal assistant, who actually knows Helen's preference and reminds Helen that she has to buy a dress for a party to come. Now, this machine knows Helen's preference. That's not just aggregation of what people normally buy. Knows a specific model about what Helen would like. And then is able to provide a personal suggestion to Helen and explain Helen why that suggestion is actually important, is suitable for her. So Helen at that point might like it, but actually might interact in natural language with the machine and say to the machine actually that she's thinking about something different. She wants to go a little bit outside the comfort zone. Now, this is very difficult natural language processing here, and the machine should be able to understand what really Helen means and use that information in order to, one, update the model that the machine has about Helen's preferences, and two, provide a more suitable suggestion for that particular context in which, mood in which Helen finds herself in. And of course, then Helen might like the suggestion in this case, and go ahead. So what is actually really important here is the natural language dialogue, communication between the human and the machine. So is the machine here there to help the specific person rather than the majority of population? So the second, let's say what happens then to Helen in the day. Helen goes to work. And let's assume that Helen is an expert software engineer. And her task is actually to control and monitor the performance of software in a space, let's say an international space station, since this is one of my past expertise. And clearly, Helen is worried about some of the data that is reading. Now, in this case, Helen could potentially interact in 2037 with an intelligent, smart, rational machine that is able, that knows the software, knows the circumstances in which the software operates, but also has a general knowledge about physics, space, and so on, and is able to analyze the data and come up with not only the detection that there is a bug somewhere, but also the recommendation of how to fix this bug. Now, here we're talking about safety-critical system. This is very hard and very difficult to achieve. And of course, if we have the interaction I was referring before in natural language, Helen might be able to communicate with the system and ask the system reassurance of why that is a good fix and whether the fix will actually impose impact on other aspects of the software. So it's that kind of trustful relationship between the human machine I'm talking about here. And the difficulty here is the complexity of the knowledge that this machine has to have and reason about, and the kind of sort of interaction that I have with Helen. So let's assume now we are at the end of the day, and Helen is actually thinking about communicating with this social network, and is actually thinking of telling what happens actually at work. Now, this is in the situation in which sometimes when you email or message something in your social network, Facebook, and you have to be careful about what you're communicating. So let's assume that there is now the intelligent social network assistance of Helen, and what is actually being doing is monitoring the interaction between the social connections that Helen has, and is able actually to learn, in this case from large quantity of data, so this is where the big data are important, the classes of people that are safe, let's say, or the one that are risky to communicate. So the machine might actually suggest Helen to be careful, because in a contact list, there might be something we can actually leak the information outside the boundary of the security, confidentiality, all right? So this is really where the help and the assistance is actually important. And the relevance here, how can we learn from big data? These are multimodal data, text, images, and so on. So clearly, it's another hard task. So I hope I give you an overview of what really this kind of idea of rational machine can give us one day. And if we think in terms of the timeline, what are we going to be? What do you expect to see? So in 5 or 10 years' time, I believe there's going to be tremendous advancement that continues to be advanced in natural language, but in this case, learning the semantics of natural language, rather than a similarity between the syntax of sentences. And that one will help advancing the dialogue and the interaction between a human and a machine. And in 10 or 15 years' time, we will see the advent of new learning algorithms. This must be hybrid learning algorithms. They not only have the characteristics of extract information from large quantity of data, but also be able to explain what they have learned. So they have must be rich architecture, able to learn rich concepts, high-level abstract concepts, as well as low-level concepts. And in 15 or 20 years' time, eventually the integration between all these different advancements will be able to give us the realization of this rational machine that are able to learn a complex knowledge, are able to scale, to extract this knowledge from large data too, and reason about the uncertainty, as I said before, and most importantly, communicate what has been learned to the humans, and take the feedback of the humans on what has been learned. So to conclude, really, the realization of this vision of a rational machine is that what we need a machine learning solution that can combine the quantitative, data-driven approach that we have at the moment that we're witnessing in deep learning with actually the symbolic, knowledge-driven learning capability that we have in symbolic machine learning. And it's only by that that we'll be able to say that we are adding rationality now on top of our digital big brain. So thank you very much.
Thank you very much indeed, Alessandra. Some fascinating thoughts developed there. Also, I'm trying to work out whether I'm going to have a table of the trustworthiness of my Facebook friends and work colleagues. Just a couple of quick questions. There's some questions coming in, and those among you are realizing through Slido that if someone asks a question, you can actually put a little like, which means that that question or thought gets to the top there. So as well as asking your own thoughts, if you think, oh, I quite like that question to be asked, then push the like button. A quick one for you, because we'll then open up a bigger discussion. Here we are. Humans are not always rational, so how much irrationality should we have in future machines?
Oh, Well,
I know you and I are fully, I know we're fully rational.
My background is in mathematical logic, so I'm a logician. So really, actually, I think they have to be able to cater for some aspect of uncertainty. That's what I talked about, all right? So rationality is uncertainty, is the unpredictability, if you like. But I actually believe that the rational machine need to be able to help humans to see common sense in what you're doing without necessarily tuning down their creativity. Right. Okay. So it's actually how we combine these two things which is difficult.
And the risk that we are all becoming neutered because part of the joy of this world is our...
No, that's absolutely not. In fact, actually, my claim is that by having this rational machine which are personalized, we actually help people to maintain their own creativity. So we are not there to unify populations and desires and wishes by doing a mass big data analysis and analytics, but we're there actually to understand what each single individual likes and needs.
Right, and so when we've done something that the machine tells us we shouldn't have done, they're just going to say, told you so? Or they're going to learn about our irrationality?
I suppose ultimately the machine is just to guide people. Right. So it's not really there to impose any kind of
just another interesting one here, which was about how you measure success and improved intelligence in these machines.
Yeah. That's an interesting question. So in the community of university academia community of artificial intelligence, I suppose that people might know in the audience the concept of Turing test. So people are thinking, okay, the moment the machine is really intelligent is when we can ask a question and answer and be able not to differentiate whether it is a machine or a human to answer this question, all right? So now there are many, people actually think Turing test is completely overtaken. There are new tests that needs to be addressed. They actually demonstrate the common sense that humans have. So, and these are much harder. They're still open. If you go in international conference on artificial intelligence, you find this test. One which is very recent at the moment is called the Wingram Schema Challenge, which is essentially consisting of providing the right answer to question, and you expose the machine to sentences that are extremely similar. The only thing that differs is one word. So if I can say to the machine, for instance, just to give an example, ground a little bit, if I can say, I cannot fit the trophy in my bag because it's too small. And then I say, I cannot fit the trophy because it's too big. So the two sentences are exactly nearly identical except for one word. So if I ask it to the machine, what is too big or what is too small, the machine currently is not able to give you the right answer because the similarity between the sentences make the sentences identical and will not be able to discriminate. So the common sense that we use when we answer this question is what machines should have. And these are challenges open there in the community that people are trying to work towards.
Okay, the conversation will continue. We've got some more thoughts emerging here, but for now, Alessandra, thank you very much indeed. Thank you.